Hi, my name is Amanda Wijntjes, and this is my Lab 2 presentation, Lines of Charge. As an introduction, the purpose of this lab was to learn about the property of charge by observing the interactions between two everyday objects. Two pieces of clear tape were first created to have the same magnitude of charge to get a general understanding about the magnitude of excess charge an object can have under normal conditions. This lab was a continuation of Lab 1 with the application of more advanced physics principles, modeling the tapes as line charges instead of point charges. The overall result of this lab was that the magnitude of charge on each piece of tape, treating the tape as a line charge, was 1.3505 times 10 to the negative 8 coulombs. This is more accurate than the point charge value, 1.30667 times 10 to the negative 8 coulombs, as a result of differences in calculation methods I'll go into later in this presentation. These were some of the physics principles highlighted, one being conservation of charge. Charges cannot be created or destroyed. Newton's laws, for every action there is an equal and opposite reaction, and when a system is in equilibrium, the sum of the forces is equal to 0. The distributed charge process, where first you break an object into pieces, find the electric field math expression for one piece, then use the superposition principle to sum electric fields of all pieces. Some of the equations used in this lab were Coulomb's law, the electric force on an object is equal to F electric is equal to Q times the electric field at the object, Q being charge. The electric field of a point charge is equal to E field is equal to 1 over 4 pi epsilon times Q charge over R magnitude squared times R hat. The gravitational force of an object can be calculated using the equation F gravitational is equal to mg. Determining U-tape charge using the pen test was one of the first things I did. Two pieces of U-tape, 0.20 meters each, were first created by quickly pulling pieces of tape off a base tape attached to a smooth surface. Two U-tapes repelled each other, and one U-tape was attracted to a negatively charged pen, so I was able to determine that the U-tape was positively charged. I floated two pieces of U-tape with excess charge next to each other and observed a distance between them of 0.028 meters. The momentum of tape B did not change once it moved d distance away, implying tape B was in equilibrium, so F net was equal to 0, one of Newton's laws. To calculate the electric force acting on tape B, the magnitude of gravitational force was first calculated. Due to Newton's laws, I was able to set F grav equal to F electric. The electric force from A on B was equal and opposite to the gravitational force acting on tape B. The point charge for the charge starting value in my computational model was 1.30667 times 10 to the negative 8 coulombs. I'll go into how I got this value on the next slide. This was my initial point charge calculation, F gravitational equals mg, and then I solved for F gravitational and found it was 1.96 times 10 to the negative 3 newtons. I then was able to set that equal and opposite to F electric and found Q to be 1.30667 times 10 to the negative 8 coulombs. I use this point charge value as a starting value when adjusting the inputted charge in my computational model. This was some of my flow script code. You can see here is where I inputted my observed floating distance. This is where I inputted the mass of one tape. This is where I inputted the Q, or my final Q charge, that it iteratively changed to get F gravitational and F electric equal to each other in my outputted computational model. This was my E field function. And this is where I created the top and bottom tape. I broke each piece of tape into 15 different segments. I then iteratively summed the segments down here, so I found the E field for each different from the bottom tape on the top tape, and then used that to get the electric force. And then at the end, I ended up creating overall arrows for F electric and F gravitational, and then also E field arrows, where you can see here. So the green arrows represent the E field of the bottom tape at the top tape location, observation location. You can see here's my F gravitational arrow and here's my F electric arrow. And then these are some of the assumptions I made in the lab. The reason I knew my Q was finally this value is when these outputted values down here finally equaled each other. I assumed each U-tape had the same net charge, evenly distributed throughout the piece of tape, and that each piece of U-tape was a line charge, one of the most important assumptions in this lab. These were some of my observations and conclusions. The electric force on the floating tape pointed opposite to the direction of the other piece of tape, indicating that the two U-tapes repelled each other, so that was correct. I then compared the line charge value versus my point charge value. So why were they different? The point charge value assumed all charge was concentrated at the center. That was one calculation. For the line charge calculation, I segmented the tape into 15 different parts, found the electric field calculation for one part, summed the 15 individual E contributions using the superposition principle. This was more accurate as it was 15 pieces and calculations instead of one piece and one calculation. The line charge is a more realistic representation as well, because Charge is not concentrated at one point on the tape. It's distributed throughout the tape, more closely resembling a line charge. Thank you.